In today's OpenGL demo, I'm showing off this physics-based rendering system. So as you can see here, we have 5 spheres in the center and then 4 light sources around the scene and this background. And if we look, there's a rusted iron material, a brick material, this plastic material, a grass material, and then a gold material. And we can fly around and we can see they each have their own reflective properties. The metal ones actually reflect the background scene onto them, while the brick doesn't at all, and neither does the grass, and the plastic only does a tiny bit. You can also see the 4 little specular dots on each of the spheres, and those are from our 4 light sources, and they're being alighted accordingly. So if we look, the top is darker than the sides because we don't have any sources on the top, and the bottoms are also a little darker. Alright, so to explain how this works, I'll first show off how we set up the specular image-based reflections. So that's on the gold and the iron, how we actually get the background to reflect onto them. So the first thing we do is we render a pre-filter map, and what we do is for in I0 to 5 we render 5 MIP levels, and then we draw them to our frame buffer's texture, and each of these we draw an array of a cube, and in our pre-filter shader, which is this one, what we do is, this is the code for having a skybox. So a cube will spawn around us, and we'll be able to move through the scene, but we'll never be able to approach the edge of the box. So it makes it look like we're in a massive room. And then our pre-filter shader, we have an environmental map we take in and a roughness. So our environmental map is the cube map of the scene around us. And then we have a distribution GGX, which calculates the normal distribution. We have hammer sleigh, which is used to get a low discrepancy sample of I for the total sample sets of N. So what that means is basically inside our, and I can show down here, inside our cube map of our scene, the background, we don't actually draw the entire thing onto it. We simply take a bunch of random samples kind of in the sphere around us, and we use those for the calculations. So as you can see here, we take 1024 samples, and for each of the samples we get a value from hammer sleigh. Then we get H and L from important sample and just a normalize, and then if n.l from these two, from this value and this value, is greater than 0, we get a distribution in D. We get n.h and h.v. Then we calculate PDF, which is D times n.h, so this value here, divided by 4 times h.v plus 0.0001, so that we never divide by 0. Then we have a resolution of 512, and that is our starting resolution of our, right here, yeah, this is the starting resolution for our BRDL loot shader, which I'll explain in a second, in our pre-filter. And then we get an SA textile and an SA sample, and this is turning that value we get from PDF into something that's based on our float of how many samples we've taken. And then SA textile takes in pi and basically calculates, it's divides by resolution squared times 6. So this calculates how big each textile is. And then we calculate a MIP level. If we ask if roughness is equal to 0, if it is, it's just 0. Otherwise, it's half of log 2 of SA sample divided by SA textile. Then we get the pre-filter color plus equal to texture LOD, so level of detail, the environmental map, L, and then our MIP level. Then we times that by n.l, and we add n.l to our total weight. Then at the end, we divide by total weight, and we return that as a frag color. So we've taken a roughness here, and this means the rougher, and we also, our roughness values are based on our MIP values. So as we can go here, we set roughness equal to I divided by 4. So each consecutive MIP level gets rougher and rougher, and the rougher it gets, the more blurry the scene will be. So I can actually show you if we go down here and we set our, now this is the code for rendering sphere. Alright, so this is the final environmental cube map that we pass in to draw the background scene for us. So we could change this to our pre-filter map, and then in our sky fragment shader, we can activate this code here, which will draw with a texture LOD instead. So I can show you if we set the level of detail to 0 and we run the scene, we get this scene here, which at first looks normal, but it's just it's not as high resolution because it's only 512 by 512, but this is what it looks like. And this is in essence what is rendered inside our gold sphere, which has a metallic value of 100%, and we'll explain that in a second. But if we increase this to 1.2, let's say, and then show it, so this is a roughness value of 1.2 and a MIP level of 1.2, we end up with this, which is a way blurrier scene. And this is closer to what the plastic will be rendering. But we can revert that for now. Go here, environmental cube map. All right, and then that's what the pre-filter does. It gets us the values and determines how blurry they should be, and it stores each of those into the pre-filter map, and it makes 5 of them. Then we pass in all 5 of these textures, albedo, metallic, normal, roughness, and AO for the 5 materials that we have, and they are up here. And we get it for the rusted iron, the brick wall, the plastic, the grass metal, and the gold. And then with those in our fragment shader, these are all the calculations we use to take those 5 values and turn them into the physics-based rendering, which is what you saw. And for right now, I just want to explain, before we cover everything else, I want to explain how the reflection works. So down at the bottom of our code, we create this vec3f, which is our Fresnick roughness, and it's this one here, Fresnick roughness, and we return f0, which is a value we get by mixing 0.04 with the base color based on the metallic value. So the more metallic it is, the more f0 will be 0.04, and the less, the more it's just base color will shine through. And then we add a max of the inverse of roughness, f0 minus f0 times the power of this clamped value between 0 and 1 of 1 minus cosine to the power of 5. And what this does is it will basically calculate how much it should reflect, returns how much the surface should reflect or refract based on angle. So a higher roughness value will mean it will reflect less because it will be multiplied by a smaller value, and a higher metallic value will mean it gets reflected more because f0 will be closer to that original value instead of just its base color. So we calculate that there, then we get ks equals that value, and then kd is the opposite of it, and then we times that by metallic. So the more metallic it is, the more it will reflect. The rougher it is, the less clear the reflection will be. And then we get max reflection level of details is equal to 4. That's just a constant. And we set our pre-filter color equal to the pre-filter map, which is that map I was showing off that has all the blurry levels of detail. We get our value of R, which is up here, and that's just a reflection of negative V, so negative view pos times the normal, or reflected with the normal. And then we set the level of detail equal to roughness times max level of reflection. So a roughness of 1 will use the blurriest one possible, and a roughness of 0 will use the clearest one possible. Then we get BRDF from our BRDF loot, and we base that on a max dot of n and v, maximum of 0, and our roughness. And then we calculate our specular as that pre-filter times f times both of the BRDF values. And then we simply add that to our ambient, which is added to our color, and we return that. And to calculate BRDF is this file here, and it will return a GL texture 2, and this is just for a quad. And then inside here we pass in Hammersley, radical inverse, import sample GGX, geometry slick, geometry smith, and integrate BRDF. All the ones before were shown off in other ones. What this one does is it generates the texture based on n.v and the roughness value, and then it returns both of them, and we use that as the frag color. So that just gives us, like, it modifies the returning reflections, but it's not based on any of the background or sky map. It's just like an extra calculation we have to do to make it look more realistic. And then if we run it, we can show all of that in action once it loads, because we do all of this as a pre-render, so it's only calculated once. However, it's all calculated before the scene loads. And you can see that the gold right here has a roughness of 0 or near 0 and a metallic value of 1. So it reflects 100%, and the reflection is very clear. Whereas the brick has a metallic value of 0, so it doesn't reflect anything. And the iron texture, parts of it have a way lower metallic value, like these rust parts, but the metal itself has a pretty high roughness value, but it also is very high in metallic, so it's a reflection, it's just not as clear as the gold. And then the plastic's kind of in the middle between the brick and the gold. You can see its reflection, it's just very faint because it has a very high roughness value, and it only has like a medium metallic value. And yeah, that's how all the reflection works. So now to explain the rest of physics-based rendering, you should click on this video here where we cover just that, and the scene only has one texture and one material. It uses a rusted iron, and it doesn't have any of the reflections. And until next time, see ya.